Okay, in the last video we talked about the binomial model, which is the most used of the discrete probability models, but there are two other models that can be used to model discrete cases. One's called geometric model and one's called the Poisson model. So we're going to talk about those two models in this video, and we'll compare the models so we can see when you would use one versus the other. So again, we'll consider a situation where we have students at a particular university that voted 60% of the time in the most recent election, but we're going to ask the question differently this time. If we continue to ask students until we find the first one that voted, then what is the probability that it's the third student we ask that will be the first one we find that voted? In other words, we're going to continue to ask to do trials until we have the first successful trial, and we're computing the probability that that first success will occur on the third trial, on the third student we ask. Okay, this situation is different from the binomial situation because we don't have a total number of outcomes. Instead, the probability of k out of n outcomes being successful here, we have the probability that the kth outcome is the first successful outcome. This problem is more about when the first success occurs instead of about how many successes occur out of a total. But like with the binomial model, we could represent this scenario with a tree diagram where y equals that a student voted. So the first student we ask either voted or doesn't vote. Now if the student we ask votes, then that's it, we're done. We wouldn't go to a second student because we're trying to continue to ask students until we find one that voted. But in the event that the first student didn't vote, then we would ask a second student, and that student could vote. And if so, that would be the end of the trial, right? Or the end of the scenario there. But if the second student didn't vote, then we would continue to ask students, and this tree could, in theory, go on forever until we found a student that voted. Okay, so the tree looks a little differently, but we can still fill in branch probabilities like we did before, 60% chance that a student voted or 40% chance that they didn't vote. And the end node probabilities would be, in all cases except the first one, some AND cases with multiplication. So the probability that we find a student voting on the first student would be 60%, the simple probability. The probability that the second student would be the vote would be we'd have one no vote, 40% chance, and then one yes vote, 60%, so 40 times 60. Probability that it's the third student would be a no with 40% times another no, 40% times a yes of 0.6. So the probability is kind of growing as we go out here. The number of factors in there is growing. And we can see a pattern in the end node probabilities. If we want to find the probability that the third student we ask is the first one that voted, we need to multiply two no probabilities for the two students that didn't vote first by the one yes probability for the student that did vote. So it would be 0.4 times squared times 0.6. We could generalize this way. It would be that the probability of success occurring on the kth trial would be failure probability to the k minus 1 power times 1 success probability, where p is success and q is probability of failure on a single trial. So this model is called the geometric model, and the reason why it's called that is because it's related to the form of a geometric sequence. If you take our formula here, we have k minus 1 failures times 1 success. If you just reverse that, it's the same mathematically as having a success probability times k minus 1 fail probabilities. If you look at a geometric sequence, like say 3, 6, 12, 24, where we're doubling every time. 3 times 2 is 6, 6 times 2 is 12, 12 times 2 is 24. If you write the sequence out, it's some starting value times 2 squared, that starting value times 2 to the third, and so on. So one of these terms, a starting value times some multiplier to a power, is the same general form as the probability of success on the kth trial, which is the reason why this is called a geometric model. Okay, so if I had the problem, the students at a particular university, we could just immediately recognize that this could be used for a geometric model could be used to solve this. The requirements for that are very similar to the binomial model. We have to have a Bernoulli trial, which is the same as binomial, right? We have only two outcomes. The probabilities have to be constant, and the probability of the trials must be independent of each other. But the last criteria is different. So the Bernoulli trial, it still has to be a Bernoulli trial, but instead of a fixed number of trials, we use specifically a non-fixed number of trials, no total number of trials we're selecting out of. Now there's actually two ways that can occur. We can actually have no n at all, like we did in the problem here, where we're just going to continue to ask an endless number of students until we find one that voted. Or there are some problems where we actually have a total number, but the problem is asking for the probability of when the first success occurs, which means even though there's an n in the problem, we're not actually using that n. Right? So if either of those things is true, effectively it's a non-fixed number of trials problem, and therefore we can use the geometric model. So for Bernoulli trials with a geometric setting with non-fixed number of trials, we can say the probability of success on the kth trial is k minus 1 failure probabilities times 1 success probability. Okay, as with the binomial model, our calculators include functions for finding the probabilities of the geometric model in a single step. They're called geomet_pdf and geomet_cdf. But because the geometric model doesn't have any fixed number of trials, there's no n, so we only have to enter the probability of success and then which trial is going to be the one that's first successful. And the C version means that the first success occurs on or before some number. These are in the same location in the calculator as the binomial PDF. They're under the distributions menu. If you scroll down, they're at the very, very bottom of the list, geomet_pdf and geomet_cdf. Okay. So the models work similarly, interpretation's a little different. Just to review the binomial and compare it to geometric, with binomial, the random variable in our model represents the number of successes out of a total. And so, for example, if we had, say, 10 flips of a coin or something like that, and we wanted to find the probability of heads, then this would start counting at 0, and it would be 0 all the way up to the maximum number n, and we would use binomial PDF to find the probability of exactly 2 out of the 10 heads, 2 out of the 10 tosses being heads. We would use the CDF version to find the probability of up to 2 being heads, and we would use 1 minus the CDF version to find the right side of at least 3 heads. So the geometric model, similar, we can make a probability model. In this case, the random variable x represents the position of the first success in a possibly endless number of trials. So there's no n here. We can just put ... at our edge of the probability model. Notice that this starts with 1 instead of 0, right? Because we have to ask at least one person. We have to conduct one trial at the minimum for geometric. So it goes from 1 up to no n, endless. Yep, and we have a geometric PDF function that gives us the probability of the first success occurring exactly at, say, 2, right? The first head occurring on the second flip of the coin, right? And there is a left-hand side geometric CDF, which would be interpreted, let's say, with coin flips, that the probability of the first head occurs on or before the second trial. So geometric CDF 0.52 would be, let's flip a coin, a fair coin, an endless number of times, and we want the probability that the first head we get is on or before the second trial. That would be a left-hand case. If we wanted to find the probability that the first head is after the second trial, the second coin toss, then it would be 1 minus the geometric CDF of 1 and 2. So it always goes from the lowest value up to and including the value you put here. There's just no 0 in the geometric case, but otherwise they work similarly. P for the exact case, C for the left side case, 1 minus C for the right side case. Okay, there's one more model which is sometimes encountered in high school and early college math classes. It's called the Poisson model. Poisson is a French word. It's named after the discoverer Simeon Denis Poisson. And the derivation for this model is not based upon a simple tree. It's not usually presented in non-calculus-based math courses. So we're just going to present the formula for it, and we're going to talk about how to use it and use the calculator functions, but I don't have a big tree sort of conceptual explanation for it. So it uses this formula that the probability that a random variable will be equal to some particular value x, and it's lambda to the x power times e to the negative lambda over x factorial, again presented without explanation. The symbol lambda It's pronounced lambda. It represents actually the lowercase l in the Greek alphabet, and what it represents here is the typical or the expected value of the random variable. So the most likely value, if you want to think of it that way. In practice, of course, we just use calculator functions to compute this rather than the formula, and the functions work the same way as the binomial and geometric versions. There's a PDF version that gives us an exact value and a CDF version that goes up to and including a value. But in this case, we don't have an n value and we don't even have a probability p value to enter. We just have this lambda value and then the k value that we're interested in. Okay, so this symbol lambda, representing the typical or expected value, sometimes we can compute it if we have a fixed number of trials. So let me give you an example of that. If we have a fixed number of trials, an n value, then you can think of this as a formula for computing lambda. That lambda is n times p. It's the number of trials times the number of successes. So let's examine that in more detail. If we flip a fair coin 100 times and we want to find the probability of getting exactly 30 heads, if we wanted to analyze this using a Poisson model, we would first need to calculate this lambda value. Well, lambda would be the expected number of heads. And so if I take the 100 coin tosses times 50%, then lambda would be 50, because we would expect usually around 50 heads to appear if we have a fair coin, and half of the 100 would be 50. So lambda represents the expected number of heads. If about half the time we get heads, then in 100 flips of the coin we would expect to get about 50 of the trials to be heads. So that's what lambda means. It's the typical value, and if we have an n and we have a probability value p, we just multiply those two to find the expected value. So we could decide to use the Poisson model. If we decided to do that, first we would compute lambda and get 50, and then we would say, I'm trying to figure out the probability that we have exactly 30 heads. Then that would be Poisson PDF, the lambda value of 50, and then 30 for the value we're interested in. We would go to our calculator and go down here to Poisson PDF and say the lambda value here is 50. And we want the probability that exactly 30 heads appear. And we would get 6.7 times 10 to the negative fourth. That e is not an error, that means exponential notation. So 6.77 times 10 to the negative fourth is about 0.00067. The way that works is you have to shift the decimal point left 4 places because of that negative. So 1, 2, 3, 4. So that's an extremely low probability, right? Now, why is that so low? Well, that's because in 100 coin tosses, 30 is a very, very specific example, right? This probability of 100% is spread over 101 possible outcomes. So any one value, like 30, is bound to be very low. Okay, now we could, because we had an n value and we had a p value, we could have chosen to use the binomial model to analyze this. We could have said, okay, we have from 0 to 100, do the same structure and do binomials PDF, 100 out of 100, probability of 0.5, that we have exactly 30, and that gives me a slightly different and a little bit lower value, 2.317 times 10 to the negative fifth. Right? So there's a very slight difference in the probability. Which one should we use? So actually, let's compare the three models. The binomial model that we learned in the last video, we can only have two outcomes. Right? The geometric model, the same thing, and the Poisson. All three of these are discrete cases that only have two outcomes, yes or no. Right? The binomial and geometric models require that the probabilities have to be the same for each trial. That requirement actually, and also the binomial and geometric models require that the probability of the trials must be independent, which is kind of similar, right? If they're not independent, then the probabilities are moving around, right? The Poisson model is more general. Actually, it does not require that the trials be independent of each other, and we'll talk a little bit more about that later. But that would be one reason why we would choose Poisson. If we felt like the probability of one trial is affecting the probability of the other, that would potentially be a justification for using the Poisson model. Okay, what about number of trials? Binomial requires a fixed number of trials, n, that's known. Geometric may or may not have an n, but we don't use it because we're looking at the, the probability of when the first trial occurs. That's successful. And the Poisson model just needs a typical or expected value lambda, but we don't need to know p or n. Okay, so when would we typically use these three models? Well, binomial is the best model to use if we have independent trials with a fixed number of trials, a known value for n, and we're finding the probability of some number out of the n. That's really the best model to use. Geometric is specifically for independent trials with a non-fixed number of trials where we're finding the probability of when the first success occurs. And the Poisson model is best used when the trials are not independent because we can't use the other two models, or when we can find an expected number of successes but we don't have an n or a p-value. Right, so really, for this problem of flipping a fair coin 100 times and wanting to find the probability of exactly 30 out of 100 with a known probability value, because a coin has no memory, there's really no way that the outcome of one flip could affect the next flip, so the trials are most definitely independent. And that means we really should use the binomial model. Okay, we could use the Poisson model, but there's no real argument against that, so we should against the binomial one, so we should use the binomial model. So let's look at an example of a problem where we really do have to use Poisson, that the binomial and the geometric model don't work. Okay, at a local supermarket, people enter the store at a rate of 30 people per hour on average. If we observe this store for a 10-minute window in time, what's the probability that exactly 45 people would enter the store during this time? Okay, so this is finding the probability of 45 people arriving. So it's a number, a count, but it's not out of a total number of people, right? The 60 people per hour is not a total number of outcomes, it's a rate that people arrive, so we don't have an n value. And because of that, it means we can't use the binomial model, so that one's out, can't use binomial. This is finding the probability of 45 people arriving, which is a count. It's not the probability of finding something such as the 45th person is the first person to enter the store, or something about the position of the first success. Therefore, it's not appropriate to use a geometric model. So that would be an argument for using the Poisson model. Also, if we think about how people could arrive at the store, they could come via automobile and be entering at completely random times that are disconnected from each other, but they could also be coming, say, via a city bus, which means if one person enters the store, there might be 3 or 4 other people that enter the store soon after that because the people are all connected in some way. They're not independent of each other because they all came on the same bus. So that means we can't really assume that the probability of a person arriving within the window is independent from person to person. And that means that only one of these 3 discrete models is appropriate. We should definitely be using the Poisson model for 2 reasons. We don't need an n and p value, which we don't have, and the Poisson model is usable when we have non-independent trials. Okay, yes, so we have a situation where we're finding the probability of a count, but we can't find an n or a p. Okay, so let's actually solve the problem. Since this is a Poisson model, we need to find lambda, the expected number of successes. Here, that's going to mean the number of people we expect to arrive on average during the 10-minute observation window. So we have a formula, lambda is np, but we can't use it because we don't have an n and we don't have a p, so there's no way for me to use that formula. Okay, but if we start with the rate that we know that there are 60 arrivals per hour, which is the same as saying there are 60 arrivals in 60 minutes. That's the same as saying we have, on average, 1 person arriving per minute, right? So if we observe for a 10-minute window, we should expect, therefore, 10 people to arrive. If typically 10 people would arrive, then that's our lambda value. Lambda is 10 people. So now that we have a lambda value, we can go ahead and draw a probability model. X is going to represent the number of arrivals in 10 minutes. Right? We could have 0 people arrive, or 1 person, or 2, or 3, or 10, or 50, or 100. It just keeps going forever. Typically, 10 people would arrive, right? But we're trying to find the probability that exactly 45 people arrive. Okay, so we could use our Poisson PDF function. Let's go ahead and do that. Poisson PDF is also in the distributions menu. It's towards the bottom, and it's between the binomial and the geometric. So Poisson PDF, because I'm finding the probability of exactly 45 people arriving. So the lambda value was 10. We said we would expect typically about 10 people to arrive, and we want the probability that 45 people arrive. So that turns to be 3.79 times 10 to the negative 16th, which is practically 0. It's extremely small. But that makes sense why it's so small, right? Because our 100% of probability is spread out over an infinite number of outcomes, right? This just keeps going and going and going. So any individual number here is bound to be extremely small. To give us a more realistic probability value to calculate, let's change the problem a little bit. Let's have the same scenario, but let's say we want to find the probability that less than 8 people arrive in the 10-minute window. So if I wanted to say less than 8 people arrive, the expected value is still 10, but that means we're finding the probability of less than 8. So less than 8 is up to and including 7. So that means I could use the Poisson CDF version, the cumulative version, where 7 is the upper boundary. So if I go to that same location, distributions, actually I'm going to scroll up. If you scroll up, it wraps around. So Poisson CDF, and lambda value is 10. We expect 10 to arrive, and we want the value up to and including 7, which would be fewer than 8. That probability is 0.2202, so a more reasonable probability number. All right, so that would be the way we would use the Poisson CDF function. Okay, so just to summarize everything, let's look at all three models. We have the binomial model, the geometric model, the Poisson model, right? The big differences are Poisson does not require trials to be independent and does not require an n and a p value because we can just calculate the typical values, sometimes using other ways, right? The big thing about geometric is it's about finding the probability when the first success occurs instead of a count, which is what binomial and Poisson are about, right? And binomial and geometric require independent trials. All three of them have the same structure on the calculator, right? There's a p version of the formula for exact cases, there's a c version for the left side, and we would use 1 minus c for the right side. And there's ways to compute by hand if we had to. The probability of exactly k successes would be n choose k times the probability of success k times the probability of failure n minus k times for binomial. And for geometric, it'd be k minus 1 fail probabilities times 1 probability of success. And then for Poisson, we would use this algebraic formula for finding that. The reason I mention those, by the way, is specifically for AP Statistics students. The AP Statistics exam often has problems that involve binomial and geometric calculations, not so much Poisson. But for binomial and geometric, they often, especially in multiple choice problems, expect you to be able to calculate it manually. They'll have answers that are in the form of these manual structures. So I wanted to make sure and mention those here. But in other classes, like honors finite brief calculus, we typically don't do it by hand. We do it with the calculator model. Okay, so that's a summary of the three most commonly encountered discrete probability models. There's one more video in this series, and that talks about the distribution of these values. If we did a PDF version across all three, what did the distributions of these look like? There's some very interesting things related to how the probability is distributed for these models.